Welcome to today's lecture. I've entitled it Making Sense, and I'd like to give credit to the neuroscientist Beau Lotto for today's images. Let's start it with a game. To win this game, all you have to do is see the reality that is in front of you as it really is. Here we have two panels, one with a black background and one with a white background. One of the dots is the same in both panels, and while you're trying to decide which it is, I'll state the obvious and point out that we can pretty much eliminate the light orange, the dark blue, and we can probably eliminate the pink and violet as well. So have you decided? Let's find out what the reality is. Here's the light blue. Of course, that's darker. How about the green? No. The reddish orange? Not the same. What about the gray? If you saw that it was the gray, then you must be a complete realist. Nearly every living organism is able to detect light. So seeing color for us as humans is one of the simplest things that the brain does. And yet, even at this most fundamental level, we see that context is everything. It's not so important that context is everything, but why is context everything? Answering this question not only tells us why we see what we see, but it tells us about ourselves, our society, and, as you will see, about geometry. Before we go too far, let's answer another question, and that is, what is color for? Here I'll show you. This is a jungle scene which shows the light reflected off of the surfaces in the scene. Do you see the predator yet? If not, he has probably eaten you already. Now we see the color spectrum, and we see that color plays an important part in helping us determine what is real. But this is problematic. If it is true that we have no direct access to our world except through our individual perceptions, this is a problem because the same image could have a number of sources. For instance, here we have a picture involving two images, same in size, same in spectral content, lumens, and what is amazing is that the retinal information that we get is identical. Here you have this, what is a lighter color, maybe an orangish color on the bottom chiclet, and a mauve or maroon color on the top. The information, though, is the same, as you can see for both. And yet it comes from two different sources. So the conclusion we draw in this is that the light that falls onto your eye, the sensory information, is meaningless because it can mean anything. And what is true about sensory information is true about information generally. There is no inherent meaning in information. It is what we do with the information that matters. Now, when I say to students that the light that falls onto your eyes is meaningless, you look around and they find it hard to believe. They say, everything I see has meaning. How is it possible for all this to be meaningless? But of course, it's not because that you're seeing the light that falls onto your eye. But what you're seeing is the brain's perception of that light. You're seeing the light in the context of years of meaning making our brains have gone through. So how do we see? We see by learning to see. And I'll point out here that this is our task in geometry, is to learn to see. The brain has evolved mechanisms for finding patterns, relationships, and associating the relationships with behaviors from interacting with the world. The most familiar we are with this is in the context of cognitive means, such as language. Now, here I'm going to show you some letter strings. I'd like you to read them for me, if you can. By interacting with our world through a sensory substitution, you're experiencing yourself literally making sense of it. You begin to hear patterns. Those patterns have meaning for you. You observe yourself as an observer while you're doing this. Here, a third of the letters are missing, but you put one there. Why? Well, in the past, putting an H between a W and an AT was useful. Here, try reading this. You sort the letters to make sense. You are in the position at this moment of actually having experienced yourself having an experience. Now, I want you to see how quickly our brains can redefine reality to make sense of things. Here I have a desert scene. Notice the one on the left is the same as the one on the right. It's just a reflection. And I'd like you to look at this dot between the two colors. You need to stare at it for about 30 seconds, which is a long time in such a short lecture as this. But let me tell you what's going on while you're staring at it. Your brain is learning that the right side of the visual field is under red illumination and the left side of the visual field is under green illumination. It's making sense of its reality. It's making a new reality for you. Now look at the lower dot. And if you had a typical response, you would notice that your brain was still looking at it as if it was under the red illumination and the left was under the green illumination. That was your new normal. What does this mean for context? I said that it's a far more interesting question why we see things the way we do than that we see illusions, or that the context matters. It's more important why we see that. I can take two identical rectangular shapes. Here we have two identical rectangular gray shapes. One is in a dark surround and one is in a light surround. And I can put them, I'm going to move them to this screen so that you can see them. We're going to view them two different scenes. I'm not going to change anything except their meaning. See what happens to your perception. On the left, the two tiles look like they're completely different colors. One is dark and one is a white. Whereas on the right, they all look dark. And yet we know that we have the same color of gray with the lights around and with the darks around on the left as we do on the right. When you see illusions, you're entertaining two realities at the same time. You're seeing one reality, the two gray squares, that look different, but you know of another reality that in fact is that physically they're the same. Taking this information together, you can create some incredibly strong illusions. For instance, here was one created by Beau Lotto where you have a bright orange on the bottom and a dark brown on the top, and yet in reality these two colors are the same. Let me show you again. Or even stronger, here I have 4 gray tiles and 7 gray tiles, and I'll show you that they're gray. Now let me remove the put them in the context, the one with the yellow filter and the other with the blue. You can see I have 4 blue tiles and 7 yellow tiles, when in fact instead of being blue and yellow they're actually both gray, as you saw before. That's pretty remarkable. The same thing that are making sense can apply to shape. Here we have what looked like two rectangular shapes from the context that they are in, which is what our brain is used to putting them in, putting them on the carpet and with the legs. You look like you have a long skinny table and a short fat table, when in fact what you really have is two squares that are the same in length and the same in width. This most common error applies to young geometry. So they say, oh, this looks like a square, therefore it is a square, and they ignore the properties that make it a square. Now, for instance, here's a very strong illusion. In the context of what you're seeing is a three-dimensional setting. One angle appears to be very wide, and the other one appears to be very narrow. Yet when I bring it into a two-dimensional setting, you can see that the angles are all 90 degrees. Your reality has been altered. This is why we are studying geometry, to learn to see, to learn to make meaning of our world. Here we have, in a three-dimensional space, what looks like a very obtuse, larger than 90-degree angle, and a very acute angle. The smallest angle is in green. And yet in two-dimensional space, they're all 90 degrees. Know this, the brain is a very powerful tool that is used for making sense of the reality around us. Information by itself is meaningless. Its meaning depends on what we do with that information. And the brain is always trying to and wants to make sense of things. We can learn to see and to put things in context. So in this course, we have a number of problem sets. Here, you see the very first problem. You have to read it. You may not know what this symbol means, but you can see it's DC, and it looks like a segment. So you can make meaning of this, being segment DC. You're supposed to make it to where PD is 3. So if you put P on here as 3, it's going to end up somewhere closer to C, a little bit farther away from D. You can do this. You can make sense of this. You may ask the question, when will I ever use geometry? The fact is you may never use it. But you will always have use for making sense, meaning making, for problem solving, for putting things in context. In this class we use math, specifically geometry, as the medium. It is black and white, unforgiving, uncompromising. It is the shortest path to learning problem solving. You can learn it from other disciplines like English and history and science, but it's just that this is the shortest way. So good luck and success.